So video 3 starts the discussion of covalent bonding, and really the rest of these videos are all about covalent bonding. Way more going on here than ionic or metallic, and way more going on than what we described in Chem 1 or in Honors Chem 1. Most of what we learned is true, but we're going to go deeper into a lot of those topics and start talking about some more exceptions. So covalent bonding happens when we have two things that have a similar attraction for electrons, meaning one is not strong enough to pull the electrons away from the other, forming cations and anions. In fact, since this is made of a nonmetal with another nonmetal, they both have fairly high effective nuclear charges, fairly high electronegativities, so they both quote-unquote want more electrons, or in reality they both have a strong attraction for more electrons. And the only way that both of these things can get more electrons is by sharing them. So they get closer and closer and closer, and eventually the electrons from each, or some of the valence electrons from each, kind of share that space between the two nuclei. So the nucleus is attracted to the shared electrons to the nucleus, and that's what the bond is. The nuclei to the shared electrons. So it's not just sharing electrons. We're kind of trying to break these misconceptions. Ionic bonds aren't gaining and losing electrons. That happens, and then the bond is cation to anion. With covalent bond, it's not just the electrons, it's the fact that those shared electrons are attracted to both nuclei, and both nuclei are attracted to those electrons. So that's important. And when these form, we can form one covalent bond, we can form lots of covalent bonds, but what happens is they tend to exist in fairly small groups of atoms called molecules. So a group of covalently bonded atoms is called a molecule, but it's not this giant repeating pattern like with formula units. There's a certain number of atoms bonded together, and that determines our name and our formula, and that's the end of our molecule. And when they're coming together, depending how many valence electrons each one has, depending how high the effective nuclear charge is, depending how many more it can attract based upon how many atomic orbitals it has unfilled, it will form either single, double, or triple bonds. And I'm sure you remember this from Chem 1. We draw single bonds with one line, double bonds with two lines, triple bonds with three lines. Every now and then you will see some textbooks and even some AP questions from various years show bonds as two sets of dots. So like this right here would be two dots, and those two dots belong both to the carbon and to the hydrogen, and that's what's happening, or that's what we're representing, that one pair of electrons is shared, two pairs are shared, three pairs are shared, but I think it's most common and probably cleanest and easiest to see and easiest to show that you know what you're doing if you draw them as lines. So we'll get into the rules of exactly how we draw these, but we want to talk about how these are shared. So what can happen is either we share these electrons perfectly, equally, or as they're being shared, one thing attracts them more than the other. So just to say it one more time, the reason these share is they both attract electrons fairly close, fairly equally, or fairly close in strength is what I was going to say. We define that as a small difference in electronegativity. You may see that written as delta En, difference in electronegativity. If there's no difference in electronegativity, then the electrons are shared perfectly equally. If there's a small difference in electronegativity, they're still shared, just not equally. If there's a huge difference in electronegativity, we make an ionic bond. So if there's kind of that intermediate, that small difference, that determines if the molecule is polar or not. A measure of how equal or unequal the electrons are shared. And it says down here that these aren't strict borders, but we have some general guidelines of whether things are being shared equally or unequally. It doesn't need to be 100% perfectly equal to be nonpolar, just very close. So a nonpolar covalent bond is where we share them equally, and the difference in electronegativity is small, less than 0.4. These values are likely to be given to you if you need exact values, but there are certain things that you should be able to know, like a carbon to oxygen bond is polar, a hydrogen to oxygen bond is polar. A carbon to hydrogen bond falls right on that 0.4 border. So a lot of times it's considered nonpolar, but it's about as polar as a nonpolar bond can be, if that makes any sense. It's right at the border. They're not totally equal, but they're still pretty close to equal. And I chose those three examples: carbon to oxygen, hydrogen to oxygen, carbon to hydrogen, because you're going to see those in a lot of compounds. So I'll just write those. Carbon to oxygen's right at the border, probably nonpolar, but oxygen to hydrogen and oxygen to carbon are both definitely in that polar range. So in polar, they're still being shared. It's just one atom attracts them more than the other. If our bonded atoms in this picture are identical, that is something you should be able to recognize and know, and it should be fairly easy and obvious. If chlorine bonds to chlorine, or fluorine to fluorine, or carbon to carbon, that is perfectly nonpolar. A chlorine has the exact same attraction for electrons that another chlorine has. That there's no question there, there's no memorization there of what the values are. That is perfectly nonpolar. If they're different, the electrons get pulled one way as opposed to the other, or more strongly by one thing than the other. And we've got an electron density map is what that would be. The chlorine has an electronegativity of about 3.0, hydrogen's about 2.1, so we have a difference, delta En, of 0.9. Once again, the exact values you wouldn't have to memorize, I just happen to know those. But chlorine's more electronegative. We know that further to the right on the periodic table. That is our periodic trend. So chlorine pulls the electrons really well, hydrogen pulls them less well, so the shared electrons, not these other valence electrons, just these shared ones right here, tend to spend more time closer to the chlorine nucleus than they do the hydrogen nucleus. That makes this end a little bit negative and the other end a little bit positive, and we use that Greek letter, I think it's a Greek lowercase delta there. So it's not a -1 and a +1 like a sodium and a chlorine or a lithium and a fluorine. It's minus maybe 0.4 or minus 0.5 or minus 0.6. And there are values we can put with this, but it's very rare or not important that you know the exact values for those things. But when we're trying to assign a number to it, or when we're trying to assign values to it, we are thinking about something called the dipole moment. Instead of just saying, well, the electrons are kind of being pulled this way, it is a numeric value that measures how big our dipole is, or how big our charge separation is. You could be given a set of data of these are the dipole moments, which one's most polar, or these are the dipole moments, which element attracts the electrons the most. So you'd be thinking about, well, these are telling me which direction it's being pulled. And if we're going to draw this, we would show that the dipole goes, there's an arrow in the direction of where the electrons are going, and then we turn the back end of the arrow, without that little tail on it, to a plus sign. So we're showing this end's positive, the electrons are moving that way. We'll use this a lot when we do get to IMFs and we think about properties. But that's just a little bit, we're sharing electrons, but what if the sharing isn't perfect? But what you really have to be strong in and review a lot and practice a lot, which we'll do, especially if you don't remember this, is drawing Lewis structures. So taking our individual atoms, like a fluorine, and thinking about how these two fluorines with their 7 valence electrons each can share them and turn into a compound. Understanding the Lewis structure lets you understand things about shape, lets you understand things about orbital hybridization, lets you understand all sorts of things we haven't gotten to yet, but it lets you correctly answer a multiple choice question without just guessing wildly. So if you are asked about covalent bonding, draw the Lewis structure. Don't just try to memorize everything, don't just try to guess. Draw the Lewis structure, and we'll practice that a lot. So the steps for drawing Lewis structures are here. I'm not going to read them to you other than highlighting one of them. So counting valence electrons, blah, blah, blah. It says here to connect your atoms, placing the least electronegative element in the center. If you just have to draw a Lewis structure to figure out how to do a problem, you do that. But a lot of times you're asked about fairly complex or slightly larger organic compounds. And what they'll do is they'll show you an example and say the bonding in this atom is similar to the the bonding in this molecule is similar to the bonding in this given molecule. Show where the single, the double, the triples are. Or this is how the atoms are arranged. Draw the electrons in. And I'll show you some examples of that in class as we go. But when you have a complex Lewis structure, they're not expecting you to be able to figure out everything under the sun here. But what is important is to follow these rules, and no matter how large or small the molecule as a whole is, be able to apply these rules and connect the atoms according to these rules. So we've got 5 steps here, and we've got 4 examples we're going to do. So like I said, I'm not going to read the steps other than using them as I go. So on number 1 here, draw the complete Lewis structure for nitrogen. So what I have to do there is think about the valence electrons. Well, N2 is each nitrogen has 5 valence electrons, so there is a total of 10 of them available. I start by connecting these things with a single bond. So in doing that, I've used some of my electrons. Now I want to put octets around everything. So I want everything to have the 8 electrons that they would need to be full and stable. And when I do that, you see I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. I do not have 14 electrons available. This one's a little weird since I don't have a central atom surrounding others, but this is a good one even though it's a little bit more difficult to start with. I don't have leftover electrons. I have not enough electrons, in fact. So what I have to do is, like it says, move electrons from outer atoms to form double bonds. And it won't let me erase this because I've done some other things, so I'm just going to kind of clean up the whole thing here. I'm also going to change the size of this so my dots are a little bit better. So now I've got nitrogen. I'm going to make it a double bond. So I've moved some of the electrons in, and as I look at what I have now, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've still used more electrons than I have available. So I'm going to move some of these electrons in, and I don't know why it doesn't let me erase. But it doesn't let me erase, so I'm going to totally delete the molecule and redraw it again. I've got nitrogen. If I draw this with a triple bond and then the 2 dots here, I have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. This nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. So I've used the 10 electrons. I started by filling this with 8, filling that with 8 after they were connected, but that used too many electrons. So I had to move electrons from the outer atom, or from these atoms, and make double or triple bonds until I've used the correct number, and each thing has 8. So as I do CF4 here, I've got carbon with 4 valence electrons. Each fluorine has 7, so I have a total of 32 electrons available for my drawing. Way more than the last one. But I put the least electronegative thing in the center, that's carbon. Connect it to 4 fluorines here. So that's step 1 and 2. I complete the octets around the outer things. So I just fill these guys up with dots. And after doing that, I see I've placed 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. That's how many I had. So step 4, I don't have any leftover electrons. I count, does everything have what it needs? Octet, 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 octet. Carbon has 2, 4, 6, 8. So that's the correct and complete Lewis structure. So I'm all done. NO plus, we would have 5 electrons from nitrogen. Oxygen has 6 electrons, but a positive charge means I have 1 fewer electron. So instead of having 11 electrons, I only have 10. And this should sound somewhat familiar. I've got nitrogen bonded to something else with 10 electrons available. So I could start by doing this, filling my octets. But when I do that, if we count them all up, and I'm not going to go to that tool because I think that's why I can't erase, but we count nitrogen's got 6 dots. 6 dots over here, so 12 dots, and 2 lines. I've used 14 electrons. I don't have that many. So I erase, I turn what I've erased into a bond. So now I have 8 dots on nitrogen, 8 dots on oxygen, then 1, 2, 3, 4 electrons in those 2 bonds. So 8 times 4 gives me 12, but I only have 10 available. Erase, erase. Now I can actually switch because I know that I'm done. Got 1, 2, 3, 4 dots. Got 1, 2, 3, 4, 5, 6 tied up in the bonds. So 4 and 6 is 10. Nitrogen has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. And when we're drawing a polyatomic ion, to show that there's an overall charge on this, put it in brackets and put the charge on the outside. Because if we didn't do that, then that would imply that we should have the number of electrons that a nitrogen atom and an oxygen atom both have. We don't have that many electrons. So the last one here is, why does it do that? Super annoying. Come back. There we go. The last one we have here is bromate ion. So bromine has 7. Each oxygen has 3. And we've got a -1, so we've got an extra electron. So we have 18 plus 7 is 25. We have 26 electrons. Our bromine goes in the center, surrounded by oxygens. Bromine's least electronegative, but also if you just have one of one thing and multiples of the other, that's a clue that that's probably going to be your central atom. So then I fill my outer electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now I have placed 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, but I have 26. So that hasn't happened yet, but this is where we get to step 4. Place leftover electrons. I had 26, I've used 24 on the central atom. Now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I've used the correct number. Oxygen has 8. Oxygen has 8. Oxygen has 8. And bromine has 2, 4, 6, 8. So I've got a complete and correct Lewis structure for that. So that's the basics of Lewis structure and some of the basics of covalent bonding. We're going to get into more advanced Lewis structures and a lot more with covalent bonding as we go on into the next sets of videos.